Oh, yeah. Okay, we're back. We're going to talk about a new thing today. It's called Power Series. Power Series is something that it's just a small step forward from what we've been doing. Um, and it is a very important block in where we're heading. It does get to the point, there's always a point in this chapter where, in chapter 12 as well, where I tell the class that it is like a trust exercise. You do sort of lose sight of where we're going, and at some point, a lot of things click. And we're not that close to where they all click yet, but when they do click, it'll behoove you, benefit you, will be in your best interest if you think hard and ask questions and think on it both conceptual and technical levels as we're taking the steps to get there. So I encourage you to do that. Every year around this time, I also teach a very like unbelievable game called Guess My Mystery Function. And every year I say this, there's not oftentimes that I make mistakes, but in this is one of the few things that I've gotten wrong. Every year I say this game is going to be sweeping the nation in a matter of time. And I'm surprised that it hasn't yet, but I still stand by that. This game is very near its tipping point, and once it hits that, it's going to be like you're going to be like the person that heard the band before the album came out, and you'll be able to, yeah, of course I've played Name That Mystery Function. I'm a master of Name That Mystery Function. And so you do want to get to the point where you know this game, the ins and outs of it, before your friend in another school district starts talking to you about, have you played Name That Mystery Function? So the way Name That Mystery Function works is I'm going to give you some things, some tidbits about a polynomial function. Like let's say f of 0 is 4 and f prime of 0 is 2. And this is where it gets fun. Then you get to tell me what this polynomial function is. And if you're thinking in your head, it might be easier to reverse the order of the terms that we normally see in a polynomial for this Name That Mystery Function game. You're thinking correctly. So this could be, it's a polynomial function of degree 1. And I believe a lot of you can see that this has got to be 4 to the 2x. Okay. What if I said f prime prime of 0 is equal to 6. Now, would you think that this is equal to 6x squared? Well, you could think of what's f prime of x here. That's going to be 2x, or sorry, 2. What's f prime prime of x going to equal? That's going to be 12. So, unfortunately, sorry, I guess this would be 2 plus 12x. Unfortunately, this mystery function doesn't get us. This isn't exactly right. You might be thinking what I need to make this is not 6, but 3. And I'm going to put that in as divided by 2. And this game can get more intense. It can get very heated. I can make it like a 4th degree or 5th degree, Name That polynomial function game. But I just want you to think on it a little bit about why we might be interested in that. Now, this whole idea of a power series is up until now, we've seen a lot of these series, infinite series, like I might say 1 over x squared. Keep in mind, this is not a function. There is no variable in there. N may look like a variable because it's a letter and because it takes on multiple numbers. However, it follows a script. It's like there's like a computer program out there that tells N that to just go from 1 up to infinity, stopping at every discrete number along the way. A variable is something that gets to move in different directions as it chooses. Okay, so a variable is something that you can insert different values into and it'll affect the outcome. So I might think of turning this into a function by just putting an x in there. And now it's a function with an infinite series in there. And this is what a power series looks like. And this, in a lot of cases, we'll be interested in for which x values does this converge and for which x values does this diverge. If we were to think about this particular example, well, x could be one, let's think of a really big number like 100, not 100, 1 million. If I plug 1 million in for x, will this series converge or diverge? It would actually converge no matter what number, as long as x is finite. I think you could use a limit comparison test to 1 over n squared. and you would get a finite number, and then that finite number would be whatever x is, and that would say that that converges. There will be situations with power series where you might get a situation like -2 is less than or equal to x is less than 4, -2 is less than x is less than or equal to 4. The power series converges only in a certain range for x's, okay? Those are the ones we typically look at because those are the ones that are interesting. You are going to experiment with power series functions today. What I want to show you is, like, you might not see exactly how I'm doing what I'm doing, but this could help you understand why this is important. So the idea is, let's say we're trapped in the middle of a jungle or a desert or somewhere with less technology than the technology that we're used to. And what we need to do is we need to build a trigonometric function, like, for example, sine of x, but the tools that are at our disposal only involve polynomial functions. This is a very easy to imagine you being in this scenario, and it's easy to imagine you being frustrated if you didn't have this last chapter, 2 chapters of calculus. So what am I going to do? Well, I could just say it looks a little bit like x. It does look a little bit like x, but only for that range there. Outside of between -1 and 1, it does a pretty good job. After that, kind of goes in the wrong directions. Things fall apart. Then let's say I'm going to add another function. Well, it looks kind of like a cubic function, so I could add -x cubed. And actually, if I turn that into a factorial, it starts to look better. So now this could be x raised to the 5th divided by 5 factorial. And you can start to see that this starts to get better and better and better. And what would be easier than doing what I'm doing is putting in a sum. Let's say sum is n goes from 1 to 3 of x raised to the 2n plus 1. And then what do I need here? Well, it goes from positive to negative and then negative to positive. So that's where I'm going to need it to be an alternating series. And I also need a 2n plus 1 factorial in here. Oh, well, that's kind of cool. So now what I could do is make it into a slider. Let's say a slider for a, and let's go from 1 to 100. And at this point, let's see, does this keep working as I go forward? This is usually where I get a lot of oohs and ahs in my class because students are impressed that I just, in the middle of a desert or a jungle without access to any trigonometric functions, was able to build a polynomial function that approximates a trigonometric function. Okay, that I would say is pretty cool. What you could also think about is just food for thought. What is f prime of x? Well, f prime of x would be equal to cosine of x. Okay, what was this function before? Was x minus x cubed over 3 factorial. Let's just leave it at that. What would the derivative be? This would be 1 minus, let's say, 3x squared divided by 3 factorial. Well, what would that be? That would be just x squared divided by 2 factorial. So how would I try to create this function? Let's turn this off, and let's see, now can I go, now this is cosine of x. Okay, now let's say j of x is equal to the sum as n goes from 1 to a of x raised to the 2n times, so I want this to go from 0, I guess, times -1 raised to the n. I think I need this to be n plus 1 because I want my first term to be positive. And then this is going to be 2n factorial. Let's see if this works. Well, let's just make it go from two. Okay, so maybe I needed this to start at 1. Well, I'm having some kind of a problem. What I want you to see is that if I did, this is a problem that doesn't need to be resolved now because um, this is getting way ahead of where we're at with this function, but I can do the same thing to approximate a cosine function, which is x raised to the 4th divided by 4 factorial minus x raised to the 6th divided by 6 factorial plus x raised to the 8th divided by 8 factorial. And I would assert that whatever mistake I was making that I couldn't figure out was something simple and easily correctable. I just don't want to do it while I'm fumbling around on the video. The idea is that these polynomial approximations to non-polynomial functions do have a very important role in mathematics and higher mathematics, and they are what's in chapter 12 called Taylor series polynomials, and they are what I'm getting you to think about with that Name That Mystery function game, in addition to putting you in a position to impress your friends once the game does start sweeping the nation. So hopefully this is helpful, and I really do encourage you to find some questions to ask when you watch this video.